Today I'm going to present you my PhD research entitled "On Robust Integration of Demand Response into Smart Grid Capacity Expansion Planning," which is supervised by Professor Olivier Bon and Eric Collage. We know that, let's start with the introduction. We know that the issue of our century is global warming. And we know that the temperature is rising because of human activities, and even small increase in the temperature has devastating effect. One way in order to cope with this issue is to increase the share of renewable sources of energy. For example, in a research which is done by International Renewable Energy Agency, they predict that if we want to keep the global warming below 2 degrees Celsius, we need to increase the share of renewables from 24% to 85% in the electrical network sector. But this is not easy because it poses challenges because the renewable energies are intermittent, so they poses reliability challenges to the network. One way to cope with this issue is to add flexibility to the power network. Flexibility to the power network is defined as the capability of the power network to respond to the change in the supply side and demand side. And the flexibility in the demand side is called the demand response, meaning that the capability of the network to abruptly reduce the demand when, for example, the price of electricity is high or when the system is in jeopardy. One important source of providing the demand response is electrical vehicles, grid-integrated electrical vehicles. They are specifically important because, first of all, they are considerable. They consume a lot of energy in the network. Secondly, because of the timing of the use, they can be controlled by the power network operators. But there are some challenges. For example, they are spatially and temporally imbalanced load, and because they have developed for another purpose to satisfy the mobility demand, any change by the power network can interfere with the operation in the mobility demand. In this research, we want to first, using the capacity expansion planning problem, identify a long-term grid investment plan considering the demand response. Second, we want to address one of the most important issues in demand response, meaning the uncertainty of the demand response. Then we want to focus on the demand response, which is provided by the electrical vehicles, and integrated the uncertainty of them into the capacity expansion planning problem. But what is capacity expansion planning problem? It is a long-term classical energy network problem that gets as input a prediction of the feature of the technologies, useful demand, fuel costs, and other resource availabilities. And it calculates the optimal investment and installation of each technologies, optimal energy procurement. And there are some generic constraints, including the network balance constraints, technology, demand, environmental, and market constraints. In this research, specifically, we focus on the R-ETEM model, energy, technology, environmental model, which is a specific capacity expansion planning problem from the family of Markov-Times model. It's a long-term capacity expansion problem with the horizon between 30 and 50 years. It's a larger scale linear programming with the objective of minimizing the total cost of the system. One salient feature of R-ETEM is that it explicitly models the demand response. And it is important in capacity expansion to consider demand response because it is as a kind of reserve capacity for the system, meaning that when we invest on providing demand response, we need to install less physical technologies in the network. Let's have a closer look at the variables in R-ETEM. There are two categories of variable strategic decisions, including the new capacity installation and planned demand response, and operational decision, including the energy production by each technology, import and export of the energy from and outside of the system, and energy transmission between different regions. The objective function is the discounted, minimizing the discounted cost of the total cost of the system, including the investment cost, fixed cost, variable cost, import, export, and transmission cost. Here are some important constraints of R-ETEM. R-ETEM has many constraints. I just mentioned some of them in order to give you an idea that what R-ETEM is modeling. We have energy balance constraints that guarantee that the procurement of each energy commodity C at each time T and time slice S should be greater than its consumption. The procurement itself includes the production of the energy, import of the energy, and the net transmission from different regions in them. We have capacity constraints that says that the available capacity of each technology is the summation of the previous added capacity to the system, plus whatever we have already installed in the system before the start of the planning horizon. And then we force that the production of each technology to be smaller than the available capacity. We have technology efficiency that relates the input and output of each technology. And here is one important constraint in R-ETEM. This is demand response constraint. This is the way that R-ETEM is modeling the demand response. In the first constraint here, on the left, you see that the procurement of energy service C, which should be greater than the total demand. And this total demand consists of two terms. The first term here is the annual demand, and this variable V here is the demand response, which optimally distribute the total demand at each period to different time slices in a day. And we define a bound for the value that this demand response can get, and this bound is around the nominal value for the demand response. And we also force that the summation of the demand response at each season to be equal to the summation of the nominal value, meaning that we are not allowing model to shift the demand response from one season to another season. We are only shifting the demand from one time slice in a day to another time slice in a day. Okay, so having this introduction, I will present you three of my papers. In the first paper, we use R-ETEM in order to identify the energy transition pathway for deep decarbonization of the Greater Montreal region. In the second paper, I will investigate integrating uncertainty into capacity expansion planning problem, R-ETEM. And in the third paper, I will focus on the demand response, which is provided by the electrical vehicle. Okay, the first paper is published in the Journal of Energies. Okay, so we know that the Quebec plans to reduce the total GHG emission to 37.5% compared to 1990 level by 2030. And in order to reach this target, there are some already in effect strategies, including, for example, spending a budget of $6 billion to accelerate the electrification in the transportation sector, and also the promoting the utilization of bioenergies, renewables, and natural gas in the commercial and industrial sectors, and also improve the performance of final energy consumption in residential buildings. But the question is that among all of these investment options, what is the best basket of options to invest in order to reach the environmental targets? In order to answer this question, we model the entire energy chain of the Greater Montreal region from resources to useful energy. Then we optimize the expansion of the system in order to satisfy the future demand and under different environmental scenarios. Why we are using R-ETEM? Because R-ETEM is suitable for modeling in a urban scale, because it has a focus on the both technologies that are generating technologies and the technologies that are on the demand side that are useful technologies. This picture shows that what is the what our model is, the ETEM model is doing for the Montreal case is modeling. As the input model, we have the useful demand in the residential and commercial sector, including heating, cooling, and other demand. In the transportation sector, we have different modes of transportation, including the private, public, train, and other. And we have also the demand in the industrial and agricultural. And also we have information about the price of the technologies and price of the resources. We model 5 geographic regions, including the Montreal Island, Laval, Longueuil, Montreal North, and Montreal South. In total, we model 130 technologies. 90 of them are end-use technologies, 8 of them are generation technologies. We model 51 energy commodities. 13 of them are useful demand, which is grouped into 5 categories. End-use technologies are a detailed list, for example, in the transportation based on different technologies, EVs, hybrid vehicles, buses, and metros and trains. And in the residential and commercial sector, we have a detailed description of technologies, for example, different furnaces, pinch, heat pumps, stoves, and other technologies. And the model output is the optimal capacity expansion planning and also the optimal investment in different sectors in order to reach the environmental targets. In this slide, we have defined different scenarios for the GHG emission reductions. The business as usual assumes that there is no constraints on the total emission. There are only already in effect policies, for example, encouraging the electric vehicles by the government. GHG1 assumes 37.5% GHG reduction by 2013 and 53% by 2015. The more stringent scenario is GHG2, which assumes 37.5% GHG emission reduction by 2013, and it linearly reduces to reach 73% by 2050. And the last one is GHG3, which assumes 44% reduction by 2013 and 93% by 2050. Here you see the result of the model in the actually figure A is the breakdown of GHG emission reduction by different sectors and for different environmental scenarios. You see here that transportation sector plays an important role even in the business as usual scenario. You see that the total emission by the transportation sector is reducing drastically even in the business as usual scenario. This is because of the already in effect technologies, already in effect policies to encourage hybrid and electric vehicles by the government. And here in the figure B, you see the contribution of each sector, commercial, residential, and transportation, in the difference of the emission between the business as usual scenario and the GHG3 scenario. Here you see the that the residential sector is playing an important role, and it takes a lot of share in the total reduction. This slide has a closer look at the transportation sector and looks at the main strategies in the transportation sector. First of all, you see that the consumption of the gasoline will reduce drastically, and it will be replaced by electricity. This is even in the business as usual scenario. This is mainly is done by investing on the hybrid vehicles in the private transportation and investing diesel, gas, and hybrid buses in the public transportation. But in the more stringent scenarios, including GHG 1, 2, and 3, the model chooses plug-in electric vehicles rather than the hybrid electric vehicles, and electric buses and biofuel buses in the public transportation sector. This slide has a closer look at the residential and commercial sector. You see that in the 2020, the main fuel that is consumed is electricity, and in the commercial sector, it is natural gas. In the business as usual scenario, in the residential sector, you see that because there is no environmental constraint on the model shifts to natural gas. But in the more stringent scenario, GIEV 1 to 3, this is the electricity will take the most of the share in the total energy consumption in the residential sector. We can see again a similar pattern in the commercial sector, and these patterns are achieved by main strategies: replacing fossil fuel furnaces with electric heat pump, promote utilization of electric heating boards, and improve the energy efficiency through insulated walls and roofs in the residential sector. So in the first paper, we used R-ETEM model in order to model the entire energy chain in the Montreal island. And we defined different environmental scenarios to see that what is the contribution of each sector in reducing the total GHG reduction. And we saw that in the residential and commercial sector, the main strategies were like utilization of heat pumps and electric heating board, and also investment in the energy efficiency of the building that reduces the total energy consumption. In the second work, we will have a closer, we will focus on the uncertainty that arises from the demand response. We know that in electrical network and in capacity expansion problem, the demand and supply should always be in balance. This is in order to guarantee this balance in the traditional network, the flexibility of the supply side was proposed. For example, we had some flexible technologies that could be online abruptly, and we had some energy storage technologies that with any deviation that we had in the either supply side or in the demand side, we could reduce or increase the production abruptly. But in the smart grid, with the increasing share of renewables, we need the flexibility in both sides, both the production and the demand side. The flexibility in the demand side is called demand response. Demand response, as I said, is considered as a reserve capacity. When we invest on the demand side in the on smart grid, we need less physical technologies to add in the supply side. That's why demand response is considered as a kind of reserve capacity. But it is challenging for planning that, especially in a long-term planning problem, because we cannot exactly estimate that what will be the contribution, what will be the actual contribution of people in demand response forecast. So in one side, we might invest a lot in physical technologies, but we will have a system with ideal technologies in most of the time. But on the other side, we might invest on the demand side, but we may have the risk of capacity shortage in the future. So the question in this research is, what is a risk-averse capacity expansion policy considering the uncertainty of demand response? Okay, so let's have a closer look at the formulation. The first equation here is from R-ETEM. This is the way that demand response was modeled. Variable V is the demand response variable that optimally chooses that what portion of the demand to occur in different time slices. This is the demand response which is planned by the network, by the supply side. But there is always deviation between what the supply side expects and what in reality happens. This deviation is captured through the parameter delta, and we let this parameter delta to lie in an uncertainty set. This uncertainty set is a classical budget uncertainty set. We introduce the parameter zeta, which is between -1 and 1. And we map the parameter delta, which itself is between minus beta and beta to minus 1 and 1. And then we force a budget here, a budget constraint here that says that only a few number of gamma number of these uncertain parameters can take its extreme value. The role of this constraint, this budget, is to control the level of the conservatism. When the value of this gamma is equal to the number of elements in the vector zeta, we have the most level of conservatism, and the model builds a lot of technology. And when this is smaller, we have a lower level of conservatism. Okay, so after introducing the uncertainty, our model will have a multi-period format. In a first step, we decide on the first stage decision. The first stage decisions are capacity expansion policy, how much to install technologies, and also the planned demand response, how much to rely on the demand response. These two decisions are gathered in variable x, and based on a seasonal period, when we have the actual information about the actual demand response, we decide on the seasonal energy procurement, which itself consists of energy production, import, export, and regional transmission. Okay, so our model will have, our robust multi-period model will have this form. We have a min-max problem. We are minimizing our decision variable x and y, and the nature is maximizing or choosing the worst scenario regarding the demand response. And also the thing that is important here is that the variable y is adaptive with respect to the uncertain parameter, meaning that at each season, first we observe the actual demand response and then decide on the energy procurement. This model is known to be NP-hard and cannot be solved. One way in order to cope with this issue is to approximate that using an affine decision rule, meaning that we let this function from any function that take, only we force it to take the affine format, and we replace this variable y with yi plus capital Y zeta. And after doing this technique, we can use the robust optimization techniques in order to reformulate this min-max problem into a minimization problem, larger scale minimization problem. And this can be solved using commercial software. So this is actually the end of the story. We have a minimization problem and we can solve it using commercial solver. But the point is that the capacity expansion planning problem itself is a large scale optimization problem. And when we use the robust optimization technique, we are introducing new variable and new constraints. So the size of the problem becomes very large. And in our case study, for example, we couldn't solve this minimization problem even after 72 hours. So we need to develop efficient solution algorithm in order to solve that. One feature of our problem is, if we look at again the problem, is that we have seasonally separated variables and seasonally separated constraint here, and they are coupled with the variable x, which is alongside the problem. So this format of our problem encourages us to use a kind of Bender's decomposition algorithm. In the Bender's decomposition algorithm, we need to have a master problem and some slave problems. In the master problem, we are keeping the variable x and also the static part of the procurement decision y. And then we will have some optimality cut here. I will explain about them. And also here we have a valid inequality, and also I will talk about that. In the sub-problem, we push the dynamic part of the decision rule. If you remember here, our decision rule had two parts, the static part, small y, and capital Y. So we push the capital Y to the master problem, to the sub-problems. So our sub-problems are min-max problem, and our master problem is a minimization problem. In order to avoid or vendors decomposition to be complex, and for example, removing the feasibility cut in our algorithm, we are assuming that there is one technology in the system, which is called uncapacitated technology. And the role of this we have a lot of this technology, and the role of this technology is that whenever for any solution for the X and Y, meaning that for any installation policy and any procurement decision, the demand can always be satisfied using this uncapacitated technology. But the point is that we set the price of this technology high enough in order to make sure that this technology is not will not be used in the optimal solution. Okay, so having this assumption, we know that any feasible solution of this constraint, ax plus by smaller than b, will be feasible in the subproblem, in our subproblems. Okay, so we implement the traditional Bender's decomposition algorithm. This Bender's decomposition is an iteration between solving the master problem and subproblems. For example, we solve first master problem and we obtain the optimal values, and then signal these values to the slave problem, and then solve the slave problem and update the upper bound, and also calculate the optimality cut, and then add the optimality cut to the master problem, and again solve this master problem, and we iterate until the upper bound and lower bound converge. But we have done two changes in the Bender's decomposition in order to further make the solution algorithm efficient. The first idea is that we are adding some valid inequalities to the master problem. These valid inequalities are associated with the last m scenarios that are identified in the previous iterations. These scenarios, this is actually a primal function associated with scenarios zeta L, and this scenario is associated with the previous iteration, which is identified in our algorithm. The second idea is that at each iteration, when we are solving the master problem, actually we are solving a robust optimization problem. So it is possible that this optimization problem has multiple solutions. One way to implementing the traditional Bender's decomposition, it is the solver that decides which solution to be passed to the sub-problems. But here the idea is that more wisely choose between these robustly optimal solution by solving an extra problem with the new objective function. And this objective function is a convex combination of the previous scenarios that are identified. So with solving this problem, we are actually obtaining robustly optimal solutions that are actually Pareto-optimal among all the robustly optimal solutions that are in our master problem. So with this idea, we are actually improving the upper bound because we are sending wiser information from the master problem to the sub problem. So the upper bound will be improved. Okay, so let's have a look at the result. In order to measure the performance of robust optimization problem, we are solving three models. The first model is the deterministic model, which assumes that there is no uncertainty with respect to the demand response. The second one is the static robust model, which assumes that there is uncertainty and we are solving the robust model, but we are assuming that there is no adaptability in the second stage decision, meaning that all the decisions need to be taken at once, and we don't have any adaptability in each period. And the last one is the RMPCA, robust multivariate conservative approximation, the method that I just described. We have the robust model, and our procurement decisions are adaptive with respect to the realized demand response. After solving these three models, we captured the first stage values, and then we generate 1,000 scenarios for the actual demand response. And here in figure A, you see the average performance of RMPCA and SRM model with respect to these 1,000 scenarios. And as you can see, RMPCA is performing better because it's suggesting a strategy which has a lower average total cost. Figure B is similar to figure A, but this time we are only focusing on the feasible scenarios, because it is possible that when we generate 1,000 scenarios, for some of them, we will have capacity shortage and our model cannot satisfy demand. We will rely on the uncapacitated technology. In order to have a fair comparison between these two models, we only are comparing the feasible scenarios, the scenarios that we don't have any capacity shortage. Again, you see that RMPCA is performing better than the SRM. Here we are measuring the worst case scenario. In the previous slide, we measured the average performance of our model. And in this slide, we are in figure C, we are measuring the worst case scenario, meaning that what will be the total cost of the system if the worst scenario happens, and for different budget sizes. And as you can see, RMPCA is also performing better than the SRM. Figure D is an interesting figure because it is showing a trade-off between the capacity shortage and average total cost. As you see here, for different size of the budget. As you see here, the SRM model, for most of the sizes of the budget, it has zero capacity shortage, because SRM model, as I said, it's not adaptive, so it's too conservative. It builds a lot of capacity, so we don't have any capacity shortage, but it comes with the high cost of the system. So in this figure, you can see that for some of these points, which is associated for different budget sizes for the budget, we can reach up to, for example, 2% capacity shortage for a lower average total cost of the system. So this figure actually gives us a trade-off between the average total cost of the system and the frequency of the capacity shortage in our scenario. And this slide is measuring the performance of our algorithm. We have generated different problems with different sizes, and these different sizes is associated with the time horizon of the model. Then we solve these models with 4 algorithms. The first one is simplex, that we use the large minimization problems using simplex. The second one is the Bender's decomposition, the traditional Bender's decomposition. The third one is the Bender's decomposition, which is equipped with solving the Pareto robustly optimal solution. And the fourth one is the one that uses both PRO solution and adding valid inequality to the system. As you can see, first of all of these Bender's decomposition are performing much better than simplex. And also you see that PRO BDVI is performing 40% and PRO BD is performing 22% better than the traditional Bender's decomposition in our model. Okay, so in this paper, first we introduced the demand response uncertainty into capacity expansion planning problem term. We reformulated this as a robust multi-period conservative approximation problem. We had multi-period decision-making structure. In the first stage, we decided on the capacity expansion, and on the next stage, we decided on a seasonal base. We decided on the energy procurement. We develop an enhanced version of Bender's decomposition to efficiently solve our model. The adjustable robust strategy could potentially reduce the average total cost of the system by 33%, and also the Bender's decomposition could improve the runtime by up to 40% compared to the traditional Bender's decomposition. The last paper is robust integration of electric vehicle charging behavior in smart grid capacity expansion planning. This work is published in the Journal of Dynamic Games. In this paper, we focus on the demand response, which is provided by electric vehicles. As I said, electric vehicle battery charging is an important load in the electrical network. First of all, because it's rapidly growing and it is considerable. It is a considerable amount of energy. And secondly, because they are temporary and spatially imbalanced load. And secondly, because they are flexible load. They can be controlled by the supply side. In this paper, first we develop a robust ETEM with the uncertainty of the demand response, this time which is provided by the electric vehicle charging load. Then we develop a charging behavior model based on the mean field gain theory in order to simulate the actual behavior of the electric vehicle users in response to the price signal that they receive from the network. And we adjust the level of the uncertainty in the robust model using the information that comes from our behavioral model. This figure shows the general idea of our problem. In one side, we have, in the supply side, we have the robust ETEM model. It calculates the optimal capacity expansion. And as a byproduct of solving this robust model, we can calculate the marginal cost of electricity. And also we obtain the planned demand response. Then we signal this marginal cost to a fleet of electric vehicles that are connected to the network. And we simulate their behavior with respect to the price signal that they receive. And then we calculate the actual demand response. Using this information, we are going to adjust the level of the uncertainty in our robust ETEM. Here is the general idea in a more formal mathematical format. In the robust ETEM, we have a min-max problem, minimizing over our decision variable. Here, the decision are using the same notation, but with this difference that variable X here is the capacity installation decision, and we are showing the planned demand as variable S. And then the maximization problem is choosing the worst scenario that can happen for the demand response. By solving this min-max problem, we can obtain the optimal value for the as a dual variable as the marginal cost of electricity production. We signal this to a demand model. In the demand model, a fleet of electric vehicles wants to minimize their total cost of consumption with respect to the price lambda star. And then this model gives us an optimal S hat, which is the optimal demand response by electric vehicle users. Having this information S and S hat, we can adjust the level of the uncertainty in the supply side. In this slide, I'm showing the charging behavior model. It is which is used. It is a linear quadratic model, and it's solved using mean field gain theory. Here, a representative agent is minimizing its total cost. Its strategy is to choose the charging profile U, and he wants to minimize to his total cost. The total cost consists of three terms. This term in the middle is the price that he pays for the electricity. U multiplied by the P. P is the price. I will explain about the structure of P, but P is a function of the average charging load of the total fleet. Here we have a cost of deviation from desired level of the charge, meaning that the person who wants to charge his battery wants to have his battery, for example, full charge in the morning, and but in the middle of the day, he doesn't care if it is full charge, but again, at the end of the day, he wants his battery to be full charge. So we are penalizing any deviation from desired level of the charge. X is the state of the charge in the battery, and A is the desired level of the charge for the representative agent. And here the first term is a quadratic term that we are penalizing fast charging. meaning that when the user uses fast charging, the battery deteriorates. So he wants to avoid this. That's why we are penalizing the a quadratic term in order to penalize the large number for the control variable. Here we have the price. The price is a function of the average charging behavior. Whenever the average charging behavior is larger than the expected, delta E is the expected load, which is assigned by the electrical network, and it comes from the R-ETEM model. So the network operator expects a level of the load whenever the average charging behavior is larger than he charges a larger value than the marginal cost of production. And when it is lower than the expected value, it is charging a lower level. This pricing strategy is to encourage people to be as close as possible to what the power network expects. And at the end, we have the state equation that says that the state of the charge at time 0 is the state of the charge at time 0 plus all the charging and discharging. U is the charging and V is the discharging of the battery. So the idea is that we solve a robust item for an arbitrary size of uncertainty. We calculate the optimal capacity, optimal values for the capacity model. And also we calculate the marginal price of electricity. Then we signal this marginal price to the charging behavioral model, and it calculates us the actual demand response. And then having this information, we are going to adjust the level of the uncertainty. In order to adjust the level of the uncertainty, we use a bisection algorithm. We use an upper bound and lower bound for the eta. Eta is the size of the uncertainty set. We are using an upper bound and lower bound, and then we choose the middle point. With the middle point eta, we solve the robust item and obtain the marginal price of electricity. And then we solve different behavioral model for each region and obtain the actual demand response. Having the information, if the difference between the actual and planned demand is inside the uncertainty set, we are updating the upper bound in order to reduce the size of uncertainty set. And if it is not on the uncertainty set, we are updating the lower bound. And we iterate this until the upper bound and lower bound of the size of uncertainty converge. Here you see the results from implementing the iteration algorithm. As you can see, after 6 iterations, or algorithm converged, and it is suggesting around 20% for the size of the uncertainty, meaning that based on the information that comes from the behavioral model, it is optimal to consider 20% deviation from what the supply side expect from what the in reality happens. Here is a sensitivity analysis which for the cost of deviation from desired level of the chart with respect to the minimum level of uncertainty. If you remember here, this parameter Q is the cost that we are penalizing, the penalty that we are penalizing that for any deviation from desired level of the chart. We are doing a sensitivity analysis with respect to this parameter to the required level of the uncertainty. Meaning that, for example, let's consider that this parameter is high. It means that the people that want to charge their battery, they don't care about the price. They don't care about the fluctuation of the price. They want to charge their battery as soon as they want. They don't care about the cost compared to this price of electricity. So in this case, because their behavior is less related to the fluctuation of the price, their behavior is more predictable, and therefore they their behavior can be predicted using, for example, the mobility data, and the level of the uncertainty required, the level of the uncertainty reduces. Okay, so in summary, I presented in today's talk my 3 papers in PhD. In the first model, I used a deterministic R-ETEM model in order to analyze the energy system of the Greater Montreal region and analyze different decarbonization pathways, and to obtain the optimal share of each sector in reaching the environmental target. In the second paper, we focus on the uncertainty which comes from the demand response, and we formulated a robust multi-period conservative approximation that could reduce the average total cost by up to 33%. And also we developed a solution algorithm in order to solve this large scale problem. Our algorithm could increase the efficiency of the solution by 40%, or reduce the solution time by 40% compared to the traditional vendors decomposition. In the third paper, we focused on the electric vehicles as a source of demand response, providing demand response. And we developed a charging behavior model and used this charging behavioral model in order to adjust the size of uncertainty in our robust capacity expansion planning problem. And our algorithm could reduce the total cost of the system by 6.2% reduction. Thank you very much, and I'm happy to answer your question, ask your question.
Thank you, Sajad.